Well, Kevin, we have Olympic fever on the show this week, and to start with, we want to talk about the International Mathematical Olympiad.
This is not one of the Olympics that they show on TV, right, with Bob Costas?
No, but they should, because they are arguably more important, Kevin, to the future, even than running and jumping off that pommel horse.
Yeah, so the International Math Olympiad, from what I understand, and I say this as a person who did not do very well in math and did not study it beyond high school calculus, but my understanding is this is the sort of the pinnacle of elite mathematics for sort of young mathematicians, right? That this is sort of a notoriously difficult test that is given out every year and that you can actually win a medal for solving problems correctly.
That's right. And for a while now, people who work on AI have looked at this competition. They've said this would be really hard to get an AI system to succeed at this thing. I wonder how long it will take. And the folks over at Google DeepMind took that as a challenge. And recently we learned that when they put their own system to this test, they were able to solve 4 of the 6 problems and earned the equivalent of a silver medal in the competition.
Yeah, this was a really big deal in the world of mathematics, from what I understand. I think it's fair to say that no one expected, or very few people expected, an AI system to be able to get the equivalent of a silver medal this quickly.
That's right. And in fact, Google DeepMind's score was only 1 point shy of what would have been needed for a gold medal. So they are already operating almost at the level of what the smartest young mathletes can do. So like you just said, Kevin, this is a really big breakthrough. And for me, it raises a lot of questions about where we go from here. Now that we're able to use these systems to solve these really novel problems that require a lot of creativity, can we actually start to generalize? Can we move beyond simple math and start to solve really hard problems in other domains? Can we solve problems related to novel physics or chemistry or maybe some of the big issues facing us in the world? So we have a lot we want to find out today about how these models work, what this means for the future of AI in general. And so to answer those questions, we've invited Pushmeet Kohli to join us. Pushmeet is the Vice President of Research for Google DeepMind, as well as the overall head of AI for Science. So let's bring him in.
Let's bring him in.
Pushmeet Kohli, welcome to Hard Fork.
Thanks for having me here.
Yeah, well, so I want to start by something that I read about your team recently in the New York Times, which is that Google DeepMind has a ceremonial gong in its office, and that the gong has been banged a lot recently. So tell us about this gong and what's been leading you to bang it.
Yeah, so I think this gong is a traditional, especially in our reinforcement learning team. And they have used it for whenever the reinforcement learning agent does something dramatic, right? It discovers something new or solves an interesting problem. And a couple of weeks back, there was the International Mathematical Olympiad, and we asked our most advanced maths agent to try to solve some of these problems. And these are incredibly hard mathematic problems that some of the best young mathematicians all over the world come to be tested on. And before this, it was felt that the current generation of AI systems were not there yet in terms of being able to solve these problems. But our agent managed to solve a bunch of these problems. And whenever it solved one problem, the team hit the gong.
I love this. I think newsrooms should adopt ceremonial gongs too. Like if someone breaks a big scoop, you just ring the gong. I think that would add some whimsy to the newsroom.
Yeah, absolutely.
Now, one of the knocks against large language models has been for the past couple of years that they are bad at math, which has been surprising to a lot of people because people think, computers, they must be good at math. But then they say, they see examples of people putting what seem like extremely simple arithmetic or algebra problems into a system like ChatGPT or Gemini, and out comes this like very confident but totally wrong answer. So why is math such a challenge for large language models? And then how did you come up with a solution to that?
Yeah, so the interesting thing about maths is that it has a set of rules. It's defined by a set of rules, right? You cannot just make things up in maths. right? Contrast it with natural language or the current generation of large language models. They are probabilistic models. They think about what is the probability of the next word or the next token appearing, right? And many things are things are possible. People sort of make things up, right? And so the model is just thinking about in probabilistic terms. In mathematics, when you're reasoning about what comes next, you have to be very precise. There are specific rules, and which makes it an extremely challenging thing because you have to be very precise in what you say. And if you have to now write a very long proof, you have to be precise in every step of that proof, which makes it extremely challenging.
Right. So, my understanding is that to achieve the success that you had this time around, you used 2 different AI models. What can you tell us about what that breakthrough was that let you perform as well in the Olympiad as you did? And please keep in mind that Kevin and I know almost nothing about math.
Okay. So there were 2 systems called AlphaProof and AlphaGeometry. AlphaGeometry was a more precise system which was focused on solving geometry problems, and it has a language in which it describes geometry problems, and it is able to do very effective search, fast search in that language. AlphaProof, our other system, is the real sort of key sort of result was that it is able to understand problems in this much more expressive mathematical language, a language called Lean. Like you must have sort of heard of programming languages, C++ and Java and Python and so on. So for maths, there is this very specific language called Lean in which you can formalize, you can specify what the maths problem is. And AlphaProof works in this language to write proofs for those problems, right? And that, by writing these proofs in a very precise way, it is able to sort of make progress and then verify that it actually gave the right answer, not just hallucinated it.
And are these technically large language models, or are they some different kind of AI system?
So the system underlying it has the same basic machinery, but how it trains and learns and how it sort of conducts the search is different. So it's more specialized towards the maths problem. And the other sort of interesting thing about it is while solving the problem, it actually learns how can it become better and better at solving this specific problem. So these are such hard problems that it tries to specialize on those problems while it's trying to solve it.
And how do you train a model like AlphaProof or AlphaGeometry? Do you just feed it a bunch of problems from like advanced math textbooks and say, okay, learn all this stuff and then go solve these proofs?
Yeah, so that's another very interesting question. Now, the thing that I was telling you about, that this agent AlphaProof solves problems in this language called Lean. And the tricky thing is that we don't have a lot of training data of maths in this language called Lean. So what you would do first is, what we did is basically we collected a lot of maths problems in English, then sort of build a translator which could translate these problems into this more specific and formal language called Lean. That gave us a lot of translations, and then we asked this agent to solve these millions of resulting problems. Right, so it was trained on all these millions of different sort of problems, and every time it was successful in doing so, it got a reward.
I've been thinking about giving Kevin a reward every time he asks a good question, just to see what that would do for the podcast. So we'll keep you posted about that. But I do want to talk about how you actually went about solving them, because me not knowing anything else, I think, well, you go to your Gemini.google.com, you copy and paste the prompt into the box, and you hit enter, and then a few seconds or a few hours later you get your result. But I'm guessing that is not actually what happened.
Yeah, it's a bit more sort of complicated at the moment. Eventually, we hope that Gemini will be at the place where you can sort of take one of these problems and put it there, and it will be able to solve it. But in this particular case, this is the real sort of cutting edge of machine learning and AI. we took these problems in mathematics, like in English. Then a mathematician sort of translated it into a lean version, which is a more formal definition of the problem. And that problem was given to the agent. And the agent then spent hours, and in some cases, for some of the hardest problem, days thinking about the problem, solving multiple variants of the problem to see if it can crack it in one way or the other way, and then eventually found the proofs for these problems.
And what are you able to see along the way? Like, is it generating outputs that you're able to review, or is it all just sort of,
It just
systems
spits out
whirring?
a number at the end.
Yeah.
4.
Yeah, so it's very interesting. Now you're asking about it. It's very interesting. What it does, it essentially tries to solve variants of the problem. So it will say, okay, there is this very hard problem. Can I make an easier version of that problem? For example, I have to prove a statement about numbers. Can I prove this statement about even numbers? Is the problem easier for even numbers, right? Or rational numbers? Or for this, let me think about proving it for this special case when the numbers are less than something, right? And then over time, it sort of starts proving these, and then once it is successful, it changes its learning sort of strategy to be able to sort of prove the full problem. So that was very interesting to see.
I want to talk about how long this system took. You just said that your system had taken as much as several days to solve some of these problems from the Math Olympiad. When real human students are taking this test, are competing in the Math Olympiad, they had about 4.5 hours for each exam, so maybe like an hour and a half per question. But your model is slower than that, which I think would strike some people as odd, given that it's a computer and computers are supposed to be fast at things, especially with this much compute in them. So what explains the disparity between the time that AlphaProof takes to solve one of these problems versus a very talented human mathematician?
Yeah, it just tells you the difficulty of the problem. Now, like, of course, we could sort of increase the amount of compute, right? And those times would be sort of smaller. But in this particular attempt, we were not trying to really minimize the amount of time. What we were trying to do is maximize what types of problems can even be solved, regardless of the time. Because before this, even if you give the system not days but months, it will not be able to solve the problem.
And am I right, Pushmeet, that while some of the problems did take up to 3 days, that some other problems your system was able to solve in just a few minutes?
Few seconds even, right? Wow. So for the geometry problems, our specialized system, Alpha Geometry, it operates in the language that's specifically designed for expressing geometry problems, and in that language, it's able to sort of solve these problems in a matter of seconds.
Sometimes these systems solve problems in ways that humans usually wouldn't come up with. There's a certain difference in how they go about solving a problem. I remember when AlphaGo was competing against the world Go champion Lee Sedol. There was this famous move 37 that everyone was talking about, where the computer sort of makes this move, and all the commentators and everyone who's like understands the game of Go is like, what was that? Like, that was a move that no one expected, that no human Go player would have made, but that ended up being sort of the correct move in that situation. Were there any sort of ways that this model was able to solve these math problems that struck you as either strange or just unhuman-like?
Yeah, so you're absolutely right. There can be many counterintuitive strategies that the agent can be taking. Now, we are still sort of digesting all the information that the agent worked out. So we have not done the full analysis yet, but it was very interesting to see all the interesting subvariants of the problem that this agent was sort of working on. So some of them maybe a mathematician might also solve it in that way, but definitely in certain cases, the way it constructed the proof was quite different.
I'm curious, Pushmeet, about the two problems that your models were not able to solve correctly. Is there a theory among the team for why those problems were harder?
Yeah, so that's a very good question. So there are different types of mathematics problems that appear in the Olympiad. There are algebra problems, number theory problems, geometry problems, and combinatorics problems. And the two problems that we weren't able to solve were combinatoric problems. They require reasoning about large solution spaces and so on. I mean, we are now analyzing what made those problems challenging, and are working on improving the agent.
Yeah, and Kevin, you wouldn't know this, but combinatorics is the branch of mathematics dealing with combinations of objects belonging to a finite set in accordance with certain constraints, such as those of graph theory.
Thank you, Casey. That I'm sure was just ad-libbed off the top of your head and not just read from a Wikipedia page.
No, I'm a huge combinatorics guy. Pushmeet, one of the big questions in AI is whether it will soon be able to advance the frontier in scientific fields by solving novel problems, maybe by coming up with a proof for an unproven theorem. How close do you think we are to that now?
Yeah, so I think with regards to AlphaProof, this is still sort of a bit away from research level mathematics, but we hope it will become an interesting sort of tool for mathematicians to use very sort of soon. Aside from AlphaProof, in the last 3 years, some of our other sort of models have already made new discoveries in mathematics. But those were more specialized sort of models, which were trying to solve a specific problem, like there is this problem of matrix multiplication. Can you multiply matrices faster? This is like a very fundamental problem in computer science and mathematics. And we were able to show that you can come up with a new algorithm which is faster than what the computer scientists knew about after sort of decades of work on that problem. And we have similar sort of results for other sort of problems as well. But in a general way, AlphaProof is probably the most general and state-of-the-art system.
I'm curious how elite mathematicians are feeling about AlphaProof and all the successes that you've had with this AI system. I remember that after the big AlphaGo competition, where the system that DeepMind had developed beat the world champion Go player, Lee Sedol actually retired shortly after that from professional Go because he basically said there was no point in trying to beat the machine anymore. It sounded like a little bit depressed about the fact that he had been sort of usurped in this way. Do you think mathematicians will see this silver medal on the IMO and go, well, why am I doing this, and just take an early retirement, hang up their calculators?
So this is a very interesting thing. Now, even in the case of Go, what we saw is that after the match, when Go players started analyzing AlphaGo's strategies, they discovered a lot of new theory about Go that they had not sort of seen, like Move 37. You mentioned that earlier, but like really exploring this unexplored part of the game really sort of energized the whole sort of community to sort of discover new lines, and people started playing more creatively and so on. Like even they were like AlphaGo style sort of games. Now, in the context of maths, if you think about it, it's not a game, right? We are trying to understand the world, and it's a very hard problem. And what alpha sort of proof or systems like this give you is basically a very powerful tool to assist in that big thing that mathematicians and scientists are trying to do, which is try to make sense of the world.
I'm curious if we could just zoom out a little bit, because obviously there are a lot of people who are excited or nervous about the progress happening in AI, but who aren't elite math Olympiad participants and don't really see the obvious connection between what you all are doing at Google DeepMind and their own lives. Can you just sort of paint a picture for us of a future where AI becomes very, very good, if not better than all living humans at complex math, what would that mean for society? What would that mean for scientific progress? Basically, why should people care about this?
So, first of all, I should say, in your description, I am one of those people in the sense that, my background I'm a computer scientist.
And you're not an athlete?
No, I'm not. I'm not a mathematician. I'm a computer scientist, and if you give me some of those IMO problems, I would struggle. And I have no hesitation in sort of saying that those are very hard sort of problems. Now, the interesting sort of thing is, what are the long-term sort of consequences of this progress? It might seem, it's a conceptual thing, like some maths sort of contest, but in the real world, it has major implications. The same techniques of giving proofs of these mathematical statements, the same type of technology can be used for understanding and proving the behavior of software systems, for instance. And if you look at basically the world today, it's run by software. This will have implications for cybersecurity. Like, we will be able to sort of prove correctness, sort of find bugs in software systems much more effectively. And so there are so many sort of downstream sort of positive use cases of the same technology.
Well, it sounds like there will soon be many more reasons to bang the gong over there.
Yeah.
Keep banging that gong.
All right. Pushmeet, thank you so much
great.
for coming on. Great to talk to you.
Thank you so much. This was super fun.
Yeah, it was fun. I loved the discussion. You guys are great.
Hey, that's the end of this clip. If you liked what you saw, head on over to our page and subscribe, and you can get the full podcast. We do a show like this almost every week on tech and the future. Head on over there now and subscribe.